Yeah, thanks for these very, very nice words. It's really an honor for me to be here. I found also this idea, besides saving money, to have 4 plenary lectures in a row very interesting, because you see all the different fields of clay science. Yeah, and I will add a little bit on that, hopefully, and also some new things. This is not only my work. I want to mention the group right now in Jena, but I also want to mention a lot of collaborators throughout the years. And the title is basically Characterization and Use of Clay-Based Nanomaterials. So as the presenters before, we are basically tackling a huge scale or a huge variety of dimensions. So I will not go to the molecular scale. I will mainly focus from the distance of surfaces, let's say a clay surface, a montmorillonite surface, over to what was also shown nicely by the presentation of Tiziano Nisana on the sorption. And then in the end, we want to predict something. So really from the angstrom to the kilometer scale, but also from the time scale, from picoseconds basically to million of years. And that is basically also putting some complexity in our system. So starting when I have chosen the title, I was, let's say, a little bit optimistic to put this all in 40 minutes presentation. If you look right now on, let's say, a word cloud, if you're just looking on nanomaterials or clay nanomaterials, then you see a lot of things popping up that I was definitely not aware of. Yeah, tissue engineering, drug delivery, biomaterials, chitosan, hydrogels, and then there comes also something like 3D printing. So then if you look even further and look just on the nanoclays itself, then you see, I mean, this is something that started somewhere in 2001. There's a lot of publications there, and there are also a lot of different topics, polymer science, yeah, chemistry, physical, then you see food science, technology, you see mineralogy, but you see also engineering, civil, and so on. So I really just give you a couple of short examples, and this is by far not complete. It's just to give you a kind of flavor. So the first thing I want to study, and this is something that my Jocelyne introduced me, and she is working basically on the medical application. That's a very interesting field. So what you do is basically you take clays as a carrier, a nano carrier, for example, anti-tumor drugs. So how does that look like? So if we look right now, and I can only recommend this very nice review on this part of nanoclays for cancer research, diagnosis, and therapy. We have the nanoclays here in the middle, and we try to coat them, we try to target them, and we try to apply this in the field. Now, what Jocelyne and co-workers did, they looked at oxine-dilomine complexes and the interaction with the bidylite structure. And the interesting thing is what you do, or what you try to do, is basically checking reversibility. Reversibility of sorption, but not in the sense that we are doing usually with metals. So here it's basically a metal organic complex, and that's the key. So we are looking only for 24 hours, yeah, because we wanted to have basically the short residence time in your body, and you want to see how much of your drug is delivered. And that's exactly what is done here, and that's a lot of what is done in this field of research. And I'm pretty sure we will hear also a lot of presentations throughout this week. What this means is that this is all triggered by properties where you are the experts. We are looking at cation exchange capacity, morphology, density of charge, particle size, and surface area. So that's basically what we have to deal with and have in mind. Another field which is very interesting is how can we use basically materials to get better mechanical properties. So this macromimetics on synthetic nanoclays, this was published in Nature Communication, and sometimes the scientific world is also really small. So this co-worker here, Felix Scha fer, I worked with him for let's say, education programs for students since I moved 2017 to the University of Jena. And I finally realized, preparing this talk, that he is already working in nanoclays. Yeah, so the scientific community is small. So what did they do? They basically looked on different aspect ratios. Yeah, you see here it's starting from a hectorite, saponite, to fluorohectorite and then a mica. And you see here the aspect ratio is very much different. And what they did basically is they used polyphenol alcohol to get a nice template of this material. So it was basically what was shown in the talk before also, so how organics basically intercalate into clay structures. And the interesting thing is two parts. On one hand side, if you look here of the oxygen permeability, you drastically change the oxygen permeability by the aspect ratio of this material. And the other thing, what is really interesting, is that you drastically change the mechanic properties of this material. So you have basically something which is a high performance material, and the additional advantage is it's transparent. So you can use that basically in many different applications. I checked a little bit further on that because I like this idea, and there was then an ACS Nano, another publication. The presentation that I gave you before this work, that was on spontaneous, basically, templating. And what they did is they did also a kind of constrained templating. They used a little bit a different material. They used sodium alginate. And what they performed was basically then this nice little texture preparates by using this alginate in the interlayer structure and addition of calcium that basically also cross-linked the nanoclays. And what they basically found out by that is, if you do not perform this and look at the spontaneous, let's say, production, then you see the mechanic properties are not so good. Yeah, this is just by these wave structures that you find here. But if you do it in this way that I showed before, then you end up with really high mechanical strength. And if you see this right now here in this presentation, then the mechanical strength is basically somewhere in between what we have as glass fiber reinforced composites or the carbon fiber composites. Yeah, so it's really interesting. And it is also, when you think about heat insulation or flame retardant properties, these materials are the way to go to. Now, the third topic I briefly want to tackle with the nanoclays is basically construction building technology. So the future way will basically be to build or construct with a 3D printer, a really big 3D printer, buildings. Now, one of the challenges is if you print this material, that it really sticks together. And what has been found is that nanoclay of attapulgite type is really stabilizing this material. And this is really one way. It's not really a high addition. It's something like 0.3% by weight of cement, and you have already really a good performance. The other thing is that when it comes to the yield stress evolution, we still have some challenges. So if we add here the clay, it is not fully clear what happens in the system. And that seems to be that, or this is at least the interpretation of these authors, that the ettringite and the nanoclay are somehow interacting. And it seems to be that this is changing the static yield stress in a way that we have right now not in mind, yeah, or we cannot easily explain. I would go a step deeper. So here we are involved. We are working in a so-called priority program on calcined clays. It's called Opus Fluidum Futurum. Guess why? Because it's a future fluid. Yeah, and this is a consortium with KIT, the Bauhaus University in Weimar, and Leibniz University in Hanover. But we want to look at the initial rheological behavior when we add calcined clays to this system. Here's just some example of PhD done in Weimar, and we added also 3 different snack types. I will not go into detail on that because I want to move in a little bit in another direction. That is trace metal uptake. So how can we use these nanoclays for trace metal uptake, and also on the other hand side, colloidal stability. That's always something that I'm very interested in, and can we also think about colloidal stability on that? So when you think about the clay in itself, then based on the aspect ratio, you have one challenge. Yeah, so you have basically the edge sides, and then you have the face or the planar sides that are in a way, when we think about smectites, negatively charged. And there were a couple of papers in the literature, I think it started with Sekor and Radke, that started to think about this so-called spillover effect. And then when you dig a little bit in the literature, 1996, Gerson Sposito, they also thought about the spillover effect, but in a way that they thought, if you see here, there's a high positive edge charge, and that spills over to the face charge. Yeah? And that basically they explained by that partly anion sorption under very low ionic strength conditions. Now, looking later in the literature, Christophe Tournassat and Ian Burke and co-workers, they basically used a kind of modeling approach, also molecular modeling approach, to predict monoclide titration data that you see here. And this worked for them quite well. Yeah, there's only 2 or 3 points that you have to make. On one hand side, you are limited by the ionic strength of your solution to a 1-to-1 electrolyte. You look also only on minor stacking. If you think about a bigger stacking, then this Poisson-Boltzmann approach will most probably not work as it is published here. So now the question is, how can we transfer this to maybe colloidal stability data? And this is something where we worked in the past, if this shows it, with a very simplistic or simple DLBO approach to calculate edge, face, 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 edge, edge interaction. And then you come up with something, so this is the critical coagulation concentration, where you have basically only diffusion-driven coagulation of colloids, and this is here right now calculated only for the edge-face interaction. And then you can see here on the black dots, these are basically the experimental data, and then you try to fit this somehow, and then you have really a broad variety, and this is basically just a quantitative approach. What we have right now done in, let's say, in an approach is basically looking at the charge regulation. So if you think about the diffuse double layer that you have of 2 silica that are approaching each other, then they will interfere, and that has an influence here on the overall attachment probability of these 2 particles and also on the surface complexation. And this is basically the conceptual idea to move this forward from a pure silica surface to a clay surface. Okay, so Tiziana mentioned that already in her talk. So we are also working, or we are working together in the Grimsel test site and looking on basically the integrity of the bentonite buffer. So imagine that you have here a water conducting feature that is directly intersecting with the bentonite buffer. And then the question is, if you have low mineralized water, is there an erosion or a particle nanocolloid release into the system? So we did this in 2 type of experiments. The one is called IBET, and you see here, this is basically barricade bentonite, outer diameter 210 millimeter, inner diameter 114 millimeter. That was provided by Posiva. This material was directly placed in a borehole where we have a water conducting feature, and we have these monitoring boreholes. Now, what we can do is then we try to monitor what is basically in these boreholes, and then it comes back to the nanoparticle. So And that is something that we set up in the years from 2017 until now. And I can tell you that was not so easy during the Corona, just to get rooms established in the way you want to have them and also then the material delivered. But what we have right now is basically a colloid nanoparticle platform, and we have also, I would call it 2 to 4D surface characterization platform with a X-ray microscope and laser-induced or laser ablation ICP-MS that we tackle. What I want to show you shortly is basically what we do with this type of equipment. This is a nanoparticle tracking analysis that we bought. It looks like a little bit like an espresso machine. And what we do with that is we basically measure colloids. And we have a high resolution CCD camera, and very simple, you can basically measure the path length of each colloid. So you basically make a single particle analysis, and then you get out of the classical Stokes-Einstein equation, you get your diameter. And then you get basically a particle size distribution of that. Nice. So we, in theory, there are some challenges with the system, but I will show you how this looks like. So we basically monitored this experiment, this IBET experiment. We merged the data, so we do a lot of single measurements, single videos, and then we just have to check if our calibration is good or not. In this case, for 3 different bentonite types, it was okay, I would say. And you see that the colloids derived are in the range of 130 to 140, maybe 170 nanometer. Now, going back to our experiment, what we did is we measured first the colloid size, and we measured this for a very long time. So right now the experiment is running something like 1,400 days. You see the main colloid size from the background. This is the grayish shaded area, and these are basically the monitoring boreholes, so the color is indicative for the size in the different boreholes. There's not so much change. But if you look at the colloid concentration, then you see our background colloid concentration, that is always increased more or less by half to 1 order of magnitude just from the colloid concentration. So with that, we can basically use this data over the long time and do a cumulative mass analysis and check how the integrity of our bentonite buffer is changed or not. And if we do so and calculate that, and there are some, let's say, criteria, buffer failure criteria in the waste management organizations here in Sweden from SKB, if we lose 1,200 kilogram out of the 22,000 kilogram in a emplacement borehole, then we have basically a buffer failure. And based on our data right now with the barricade, we would expect something like 118,000 to 150,000 years that this is stable. Yeah, so okay, it's only just one experiment, but this is basically the number the waste management organization wanted to have. Now, what we can also do is we can look on the in situ parameters itself. We did another experiment. Here, it is a different clay. It's the Fabex bentonite that was provided by Ziermatt. And we looked here beside, there were a lot of different things done. So we have emplaced radionuclides here in these glass vials, but we have also looked on here the interaction of a water conducting feature with the pure Fabex bentonite. And we had the chance here, because the diameter is smaller, it's only 83 millimeter, to overcore it. And then with EMPA in Switzerland, we basically looked on the data. So what you see here right now is basically a video of the blue is the shear zone. Maybe I can just show it again, if this works. Doesn't want to work. Okay, but there was also a yellow color, and the yellow color gives you basically some idea of erosion. And we see at some parts that we have really a focused erosion in the contact from the shear zone to the compacted bentonite. And also that we can use basically for some estimation of the long-term integrity of this material. Okay, the other thing that I wanted to mention is there's a lot of, maybe not here this week, but 2 weeks ago at the Goldschmidt conference, there's a lot of work and research on nanoparticles and basically using single particle ICP-MS. So you can use the ICP-MS, depending on what type you have, for basically directly injection of the colloids into your plasma. And by that, you can basically element-specific map what are the sizes of these colloids. So the only challenge that you have is, okay, you have a background signal, that is basically your dissolved element. And then on top, there are these spikes, and these spikes are your nanoparticles in the system. That sounds, first of all, simple, but for some cases, and I will show you, then the threshold setting is not so easy. Okay, and then you have separated basically your particles from the leftover background, and from that you get a particle size distribution. So this is very nice, because then you can also think about the element distribution, for example, calcium to silica ratio, if you think of CSH phases, your quantification, size distribution, and the particle number concentrations. So you can even, because you see here, this is a group in Oviedo. We are also thinking about basically having a single cell, so that we use every bacterial cell and directly measure the content of metals in this cell. But this is not today's topic. Now, this functions really nicely if you think about gold, because in gold or silver, you have almost no dissolved background. So this threshold setting is very easy. Yeah? And that's why you find also a lot of literature on gold and silver nanoparticles. And also for us, it worked quite nicely. But if you go then a step further and want to analyze, for example, silica, then you have to set basically a good threshold in the system. And you see here, then we have this basically the standard deviation plus 3 SD, 4 SD, or 5 SD, and then you see you move the background always a little bit up, and you end up, these are basically the particles that you have. And for the reference material, it works quite okay. So, and then the idea was, okay, what is about our clay minerals? And for the clay minerals, I have to say we are still in progress. So we have some nice marked clays, but you see here, if you go to the alumina or the silica signal, then we are okay-ish with the size, and the number is also somewhere in the ballpark, but we have, for example, for magnesium or for iron, we have still some challenges to see. Okay, with that, I would like to switch a little bit and go to the field. So we have a lot of field sites that are contaminated, and how can we use basically nanoclays or composite materials to remediate these sites? This is a collaboration with a group from Gopala Daba from ISA Golgata, where we have basically contamination not only from heavy metals but also from organic dyes. And here we are going in the direction that we are basically using not only the nanoclay, but using the nanoclay with other materials. And then you have a really huge portfolio that you can think of. You can, for example, look at fibrous materials, apatite. You can think about clay and carbon supported materials. And that's exactly what we wanted to do right now. Yeah, so we look on this because we have a contaminated site that has really, if you look here on the chromium concentration, we are in the order of 10 to 13 milligram per liter with a total dissolved solid content that is around maybe 0.8 gram per liter. So now, what we are doing is we do a kind of synthesis. So we have on one hand side the bentonite, on the other hand side we use biochar. Why biochar? Because that is basically a waste product in India. So we can have this directly, and this is basically also a cost saving. And then we basically do this type of synthesis, and then we have clay biochar nanosilverland iron composite that Gopala named nanotrident. And this is how it looks like, basically, this material. Yeah, if we look with TEM, and these are basically the silverland iron nanoparticles. Now, when we think about remediation of a site, then the interaction has to be fast. So right now we are not looking on the desorption processes, we are looking on the sorption processes. And what we did with these materials, we looked also on the sorption, and you see for the chromat removal, within 30 minutes we have 90% removed, just looking at the sorption kinetics. And with the methylene blue, it's basically even faster. Within 2 minutes we have 90% removed. And the good thing is we also tried to use that in column experiments, and you can see that you have basically also an approach to purify your wasted solutions. One is with deionized water, the other one is with the wastewater from the site. So we see that this could be a way forward for remediation strategies. Another way which you can approach is basically just to take the clay itself with the iron nanoparticles and use different clays. And that's also something that we did in ISA, in Golgata. So we used the 2-to-1 clay and the 1-to-1 clay. And then on one hand side, we have basically silverland iron colloids that are 6 to 7 nanometer thick in the interlayer. And on the other hand side, we have that on the surface. And the interesting thing is, with this combination of both, you see that you can, on one hand side, get the anions out of the system, and on the other hand side, get also the cations out of the system. And that is exactly what we wanted to have. And so basically, with a combination of both types of tuned nanomaterials, we can go under the drinking water levels for this contaminated water for all these 4 metals. Now, contaminated transport is one thing. The other thing is natural processes, and there are also a couple of presentations and sessions that are thinking about transport, natural transport. And if we think about natural transport, we always have in mind the critical zone. What do I mean by that? Right now, if we think about transport processes from the surface towards the underground, then the question is, how deep does basically the surface signal penetrate into the subsurface? That's one question. The other question is, and this is something that we are facing more and more, this event-driven system. So we have climate change. I hope everyone is right now convinced that something is changing. And we are thinking of how this dynamic basically changes also the subsurface. And the third question is, how does land use, land cover, or the geology basically drives the underground microbiome and also transport processes. So what we are doing, and I hope this works, is basically that we are looking with engineered clay nanoparticles. And I come to this point in just a minute. How is the transport of clay, that is a compartment of the soil seepage, into the groundwater system? Is this a pathway or not? And on the other hand side is the trace also, what is the role basically of rock reactivity on trace metal mobility? And if you see the microorganisms in the deep underground ecosystem, then we have also the question if this triggers then also the microbiome in the underground. Now, when I think about engineered clay nanoparticles, then this is basically the collaboration with a group in Mulhouse with Jocelyn Brentley, because they have nice synthesis routes where you have metals directly in the octahedral sheet, and we can use them. So you see here, for example, a measurement of a field flow fractionation with ICP-MS, and the red signal is basically the zinc signal, and the black signal, that is the aluminum signal, And if you look there on the ratio, you see this is nicely a nice ratio over the whole size distribution. So you basically have it fully in the octahedral sheet, and it is basically there. Now we can think then about colloidal stability. We can also think about organic interaction, and we can think about the morphology of the fracture. And this is something that is basically driving the system. Yeah? If you think right now about the porous media, and this is right now a core that we have of one of our sites, then we look at the metal transport, yeah, on our engineered nanoparticles, and the nanoparticle transport through, for example, such a core. And we look on the other hand side also on the influence of the microbial community. So, before ending my presentation, I wanted to make basically future challenges. So where I see the challenges for the future. So basically outside the weather is really challenging us. Yeah, and you see also this is from Al Jazeera. So from the 21st to the 25th of July, the weather forecast, it will be even hotter the next couple of days. But what I also wanted to show you is if you look at this map from the World Meteorological Organization, then you see this was the map from the 1st of January 2023, all Europe. And this is here the deviation of 8 to 10 Kelvin. All over Europe, except some regions in Scotland and in Scandinavia, they were a little bit cooler, but basically all was driven by hotter climate. Yeah. So, and it's not only hotter. What you also see, and I think Italy was hit hardly this spring, that we have these extremes. We have extreme flooding events, yeah? And this is basically another challenge. And how to simulate that, and in my case, as I'm applied geology, we have also to think about remediation strategies, yeah? And I give you one example. So we basically work on sites that are already remediated. So this is with the Wismut GmbH and AFRI together, where we are thinking of, so we have a lot of sites in the state of Thuringia. This is basically remediated former uranium mining sites. And how did they remediate the site? Basically, you have the maize material, and then you have a storage layer on top. Yeah? And the storage layer can right now look as a single layer, a double layer, and sometimes you have an HDPE foil in there. But let's focus on that. So what happens right now if we have these extreme storm events? Yeah? So the extreme droughts. Basically, what we endanger is here, this surface coverage that is there. And how can we basically go in a new direction, or new, I would not call it new, because these ideas are already around for nutrient transport. So what you can use the nanoclays, and you add basically mycorrhizas or fungi. And by that, you stabilize, and you see it here, you stabilize this material, you have a moisture control, and on the other hand side, you have also an erosion prevention in this system. And I think this is something that we are currently working on in a new project together with Wismut and AFRI to see if this is a way forward to stabilize not only the sites in Germany, but we have a lot of former mining sites where we basically will have this challenge. Okay, and with that, I'm at the end, and I wanted to thank the different project funding agencies. You see, there's also a lot of groups like the Jena School of Microbial Communication and the Max Planck Institute for Biogeochemistry. So this is also a strong part of our research right now. And just to, maybe there's someone here in the room who is interested in a PhD. Okay.